NASA has released a new wave of images from the James Webb Space Telescope, and they are already reshaping our understanding of the universe. Among the first photographs, distant galaxies appear as faint specks of light, signals that have traveled for more than 13 billion years to reach us. What Webb has revealed is not just light from the past, but the architecture of the early cosmos itself, a view into an era when the universe was still young and raw. When Webb focused its infrared gaze toward the edge of the observable universe, it uncovered galaxies far more organized than anyone expected. For decades, astronomers believed early galaxies were chaotic, shapeless clusters of gas and stars. Instead, Webb's images showed well-formed spirals, structured starburst regions, and even the influence of supermassive black holes, all appearing just a few 100 million years after the Big Bang. This discovery alone forces a dramatic rethink of how quickly matter gathered into complexity. If galaxies were already massive and structured at this stage, then the timeline of cosmic evolution is compressed. Dark matter, thought to be the invisible framework upon which galaxies form, may have played a far more active role than predicted. Alternatively, forces we have yet to uncover could have accelerated the process. Webb's revelations have turned what was once considered the slow dawn of structure into something more explosive, a universe racing toward order with startling efficiency. Even more astonishing are Webb's views of proto-galaxies colliding and merging in the distant past. These interactions reveal gravitational dynamics in unprecedented detail, tidal forces stretching gas into luminous arms, bursts of star formation igniting like firestorms, and galaxies growing more complex as they devour one another. Rather than a quiet beginning, the early universe appears to have been a place of violent transformation. Spectroscopic instruments on Webb have added another layer of insight by detecting the chemical fingerprints of ancient stars. The presence of elements like carbon, oxygen, and iron, materials forged in stellar furnaces, suggests that several generations of stars had already lived and died within the first few 100 million years. This pushes back the timeline for stellar evolution and hints at how quickly the universe seeded itself with the ingredients for planets, and eventually, life. Webb has also begun to unravel the mystery of reionization, the epoch when the first light pierced through the cosmic fog of neutral hydrogen. Its sensitivity to ultraviolet radiation from early starbursts is allowing scientists to trace exactly when and how this transformation occurred. What was once a vague chapter in cosmic history is now being written with precision. The telescope's observations don't stop with galaxies. It is uncovering massive halos of diffuse gas around them, offering clues about the cycle of matter as it flows in, fuels star formation, and is blown back out by supernovae. It has also revealed vast intergalactic filaments, threads of dark matter and gas stretching like a skeleton across the universe. These structures were expected, but their maturity so soon after the Big Bang suggests that gravitational clumping was not only fast, but remarkably efficient. One of the most striking findings involves black holes. Webb is detecting evidence of supermassive black holes that existed much earlier than predicted, some weighing millions to billions of solar masses. Their rapid growth defies current models of accretion, raising the possibility of alternative formation mechanisms such as direct collapse. These early giants appear to have grown alongside their galaxies, suggesting that black holes and galaxies have always been locked in a mutual dance of evolution. Gravitational lensing has added to the drama, with light from ancient galaxies bending around intervening clusters. These distortions not only magnify faint, distant objects, but also expose the hidden distribution of dark matter, allowing astronomers to map the invisible scaffolding of the universe with new clarity. What Webb is showing us is not just a universe slowly awakening, but one bursting with activity almost from the start. It challenges every assumption about the pace of cosmic evolution and points to a cosmos that is more interconnected, efficient, and dynamic than ever imagined. The telescope has only begun its mission, Yet already it has reframed our place in the story of creation. Every photon Webb collects is a whisper from the beginning of time, a message that crossed billions of years to reach us. These images are not just scientific data. They are portraits of creation itself, evidence that the universe rushed into complexity almost as soon as it began. With each new observation, the telescope isn't just rewriting textbooks. It is redrawing the boundaries of human understanding, bringing us closer to the moment when darkness first gave way to light. The James Webb Space Telescope is beginning to detect some of the faintest and most distant galaxies ever observed, tiny dwarfs and proto-galaxies whose light has traveled for more than 13 billion years. These dim structures, barely visible even with Webb's long exposures, may hold the key to understanding how the universe built itself piece by piece. They appear to be the seeds of larger galaxies, merging and combining in a process called hierarchical assembly. Their abundance at the edge of the observable universe suggests they were crucial to cosmic reionization, their sheer numbers making up for their faintness, providing enough ultraviolet light to transform the early cosmos from opaque to transparent. But Webb is not only showing galaxies, it is revealing the environment between them. By analyzing how the light of distant quasars filters through the intergalactic medium, astronomers are reconstructing its composition and history. This thin gas filling the space between galaxies acted as the raw material for new stars and as the stage where black holes and galaxies reshaped matter through feedback and radiation. Webb's spectroscopic data is showing how this environment changed over time, painting a detailed portrait of the interplay between galaxies and the cosmic web around them. The telescope is also helping to assemble a timeline of cosmic history. By capturing galaxies at slightly different redshifts, each at a different stage of development, astronomers can piece together a slow-motion film of the universe's growth. From the birth of elements to the clustering of matter, to the emergence of stars and galaxies, Webb is allowing us to witness the grand transformation of the cosmos. Yet as we study the observable edge, the question lingers: what lies beyond? The telescope cannot see past the limits of the observable universe, not because nothing exists there, but because light has not had enough time to reach us. The boundary is not physical but temporal, set by the speed of light and the age of the cosmos. Still, Webb has brought us closer to that limit than ever before. What once appeared as a foggy horizon is now revealed as an intricate mosaic of ancient light. And even if the regions beyond remain hidden, Webb's discoveries suggest they too must be rich with structure and mystery. The telescope's data is also forcing cosmologists to revisit fundamental assumptions about the universe itself. Subtle anomalies and unexpected alignments in Webb's observations are raising new questions about cosmic inflation and the geometry of spacetime. Is the universe perfectly flat, or does it curve slightly across the largest scales? Could it loop back on itself in a closed shape, or stretch endlessly without end? With each precise measurement of galaxy clustering and light distribution, Webb edges us closer to answers that have eluded cosmology since its earliest days. The reason Webb can uncover such faint, distant signals lies in its design. Positioned at the second Lagrange point, shielded from Earth and Sun, its instruments remain at frigid temperatures. This allows them to detect the faintest infrared whispers with little background interference. The edge of the universe is faint, diffuse, and difficult to study, but Webb was built precisely for this task. And yet, this is about more than technology. At the heart of Webb's mission is a deeply human drive to understand where we came from and what lies beyond the boundaries of our knowledge. Each photon it collects is a messenger from the dawn of time, carrying stories of creation and transformation. As the data accumulates, some of our most established theories may need to be rewritten. Perhaps unknown forms of matter or energy influenced early galaxy growth. Perhaps the laws of physics themselves shift under the extreme conditions of the young cosmos. Already Webb is showing that the early universe was not a slow climb from chaos to order, but a dynamic, rapidly evolving place. Gas was flowing in and out of galaxies, driven by powerful winds from starbursts and black holes. Heavy elements were already being forged, scattered, and recycled into new stars. Globular clusters, the ancient, tightly bound spheres of stars, are being spotted in their formation stages, hinting at how such systems emerged from the turbulence of early mergers. Webb has even begun to capture the light of the first quasars, powered by voracious supermassive black holes. Acting like cosmic lighthouses, their beams cut through the intergalactic medium, revealing the structure of matter along the way. These quasars also flicker with variability, hinting at instabilities in their accretion disks or interactions with nearby stars and gas. By studying their patterns, astronomers are uncovering the physics of black hole feeding at the dawn of time. Even more remarkable are Webb's observations of galaxy mergers and tidal disruptions already underway just a few 100 million years after the Big Bang. The stellar bridges and stretched arms of these systems are evidence of hierarchical growth in action. Some galaxies at these distances even show hints of rotation and disk-like stability, far earlier than predicted. This challenges the idea that early galaxies were chaotic and unstructured, suggesting equilibrium was achieved much sooner in some regions than theory allowed. And then there are the surprises. Webb has detected isolated dwarf galaxies that appear to exist independently, without nearby clusters or filaments. Their existence suggests that some regions of space allowed galaxies to form in isolation, untouched by the gravitational chaos of merging environments. These solitary systems may provide vital clues to the role of local conditions in